Transformer training executes as a rigid, highly orchestrated mathematical process on raw silicon. Success depends on balancing millions of simultaneous inputs while making precise singular adjustments to the underlying weights. This diagram outlines the architecture of our subject, a decoder-only transformer based on the nano-GPT model. Note the parameter statistics on the right. Our objective is to track the exact mathematical lifecycle of a single training iteration, step by step from the moment a batch of text is loaded to the final weight update. The primary physical constraint of this system is memory. When multiple tokens are processed at once, there are no per-token copies of the model. Every token routing through this specific transformer block queries the exact same physical weight tensor in memory. To understand how this works, we have to strip away the hardware abstractions, forget about threads and streaming multiprocessors, and strictly follow the 6 sequential phases of this mathematical pipeline. Tracking this strict sequential process is the only way to see how massive models actually learn without collapsing into computational chaos. Phase 1 loads the batch. We use a micro-batch configuration, a batch size of 2 and a sequence length of 4. These text tokens convert into integer IDs. Alongside them, a matching target tensor holds the correct next token, offset by exactly 1 position. We then move to phase 2, the forward pass. All 8 positions from our batch are processed in a single, massively parallel matrix multiplication. On the left, inputs flow upward, reading the shared weight tensor simultaneously. The causal attention mask prevents them from seeing future answers. Tokens only attend to earlier positions and themselves. Brown attends to the, quick, and brown, but cannot peek at fox. Note that specific detail. A token always attends to itself in addition to the earlier positions in the sequence. Because every position's output is computed in this single forward call, every position functions as an active training example at the exact same time. This parallel structure is exactly why transformers are so highly sample efficient. At the very top of the transformer stack, we reach phase 3, the loss calculation. Each of the 8 individual positions independently outputs a probability distribution across the entire vocabulary. In the middle panel, cross-entropy is calculated against the target token at each position, generating 8 separate loss values. We do not sum these values. Instead, as the highlighted equation shows, they are mathematically averaged into a single, unified scalar value. Why must we average these values instead of simply adding them up? If you used a raw sum, changing the batch size would violently scale up the total loss magnitude. Doubling the batch would double the effective learning rate, destabilizing the entire network. Averaging keeps the parameter update scale invariant. This ensures the training run remains stable across any GPU array, regardless of how the batch is shaped. Phase 4 initiates the backward pass. Backpropagation traces that average loss signal back through the network using the chain rule. On the right panel, you can see the autoGRAN engine mechanically walking the forward operation graph in reverse, passing the error signals, the red delta boxes, downward. There is a vital memory constraint here. To compute these specific gradients, the activation cache generated during the forward pass must be retained in VRAM. In phase 5, gradient aggregation, per-token errors translate into weight changes. The 8 purple gradient contributions flow into the central orange summation node. They are summed and then divided by the batch size times sequence length, matching our earlier loss average. This process yields 1 master gradient tensor, perfectly matching the shape of the target parameter. Finally, the Atom W optimizer utilizes this single master gradient to execute exactly 1 unified parameter update. 8 separate tokens generated unique error signals, but the actual physical weight tensor is only modified once per step. This prevents conflicting data from overwriting itself. Phase 6 is cleanup. The training cycle is complete. The hardware prepares for the next batch. The massive activation cache we needed for backpropagation is finally dumped from the GPU VRAM. The parameter gradients are formally zeroed out, leaving only the newly updated weights persisting in memory. This 6-phase sequence maps directly to PyTorch: load tensors, run forward pass, average cross-entropy, compute gradients, step optimizer, and zero memory. Looking at this concise code block proves that large language models operate on highly disciplined, iterative tensor manipulation. When users interact with a language model, text is generated sequentially, 1 word at a time. This is standard inference.
But if engineers trained massive models using this slow, sequential process, it would take millennia. Instead, training relies on a mechanism called teacher forcing. Because the entire training dataset is already known, massive grids of tokens are passed through the neural network simultaneously. This allows the system to process every token position at once in a single, massively parallel matrix multiplication. During this parallel forward pass, the model strictly prohibits the use of a key value cache, the memory shortcut used during inference. All intermediate activation states must be retained in active memory. Discarding them would sever the pathways required by the autograd engine to perform backpropagation, making it mathematically impossible to compute gradients and update the network. Because all tokens are processed at once, the system applies a causal attention mask. This is a strict mathematical barrier that blinds every position to any future tokens in the sequence. It forces the model to learn autoregressively, ensuring the word brown can only attend to quick and the, rather than cheating by looking ahead to fox. This parallel masked operation means every single token serves as an independent training example simultaneously. It is highly sample efficient at the microscale, but when applied to an architecture containing billions of parameters, this exact mechanism creates a devastating, physically impossible hardware limitation. The absolute physical barrier to scaling a language model is not strictly raw computational throughput. The primary constraint is the capacity of the high bandwidth memory, or HBM, on the accelerator hardware. This diagram illustrates the memory constraints of a typical 24 GB consumer GPU. The static memory footprint to simply load a model from mixed precision training requires exactly 16 times p bytes, where p represents the total parameter count. The foundational model weights and the gradients computed during backpropagation are stored in 16-bit precision. Together, they require 4 bytes per parameter, consuming a small, manageable fraction of the total memory budget. The dominant consumer of memory is the Atom W optimizer. To prevent arithmetic underflow and maintain numerical stability during training, Atom W must retain a primary master copy of the weights, alongside running estimates of momentum and variance, entirely in pure 32-bit precision. Applying this to an 8 billion parameter architecture means the static optimizer states alone require roughly 96 gigabytes of memory. Simply holding the dormant model prior to any training requires approximately 128 gigabytes of VRAM. That 128 gigabytes does not account for the dynamic memory required for temporary activations. As the sequence length grows, the activation memory footprint expands rapidly, driven by the quadratic nature of the attention matrix, where the sequence length is multiplied by itself. A top-tier consumer GPU contains a maximum of 24 gigabytes of VRAM. Loading even the foundational state of an 8 billion parameter model onto a single device is impossible. The model's matrices must be mathematically shattered and distributed across an interconnected supercomputing cluster. To overcome single-device memory limits, engineers utilize tensor parallelism. Instead of storing the entire model on one chip, this architecture solves the memory barrier by physically splitting individual parameter matrices across multiple devices. This diagram shows a column-wise partition. The weight matrix for the attention block is divided vertically. GPU 1 takes the first half of the attention heads, and GPU 2 takes the second half. Because both GPUs receive an identical copy of the input tensor, they execute their dense matrix multiplications entirely independently. To reconstruct the final output, the subsequent linear projection layer is partitioned row-wise. This aligns the computation with the previous column-sharded inputs, allowing each device to perform dot product operations on its local partial results. After computing the row-wise split, each GPU holds an incomplete fragment of the final matrix. To resolve this, the devices execute a distributed all-reduce operation over a high-speed NVLink interconnect, summing their partial fragments into a complete output matrix. This precise pattern of a column-wise split followed by a row-wise split creates a highly efficient compositional unit. It requires exactly 4 all-reduce synchronization barriers per transformer layer. Tensor parallelism efficiently shards the massive linear matrices, but it leaves operations outside of those dense projections, like layer normalization and dropout, fully replicated on every participating GPU. This redundancy creates a new, severe activation memory bottleneck.
When training with large context windows, maintaining an exact duplicate of the input sequence on every GPU to process nonlinear operations quickly exhausts the remaining VRAM. Sequence parallelism extinguishes this inefficiency. By partitioning the input tensor strictly along the sequence dimension, each GPU takes absolute ownership of a specific fraction of the tokens, computing operations like layer normalization independently and saving massive amounts of memory. As the data approaches a column parallel attention block, which mathematically requires the full sequence to execute, the framework triggers an all-gather operation. The devices rapidly share their tokens to reconstruct the full sequence locally on the chip, just in time for the heavy matrix math. As the data exits the row parallel projection, the framework replaces the standard all-reduce with a reduce-scatter operation. This single step simultaneously aggregates the partial sums and shatters the sequence back into memory-efficient fragments for the next layer. This sharding philosophy is extended to the optimizer itself, using zero-data parallelism, systematically partitioning the massive atom W footprint across the cluster. By layering tensor parallelism, sequence parallelism, and zero-state sharding, engineers eliminate both the static and redundant memory walls. The hardware is finally clear to process significantly larger context windows. Yet, distributed sharding does not resolve the core mathematical flaw of the transformer itself, the scaled dot product attention mechanism, which computes the interaction between every single token and every other token, creating an n-by-n matrix. This creates a catastrophic hardware input-output bottleneck. A GPU has a high-capacity but slow memory pool called HBM and a tiny, ultra-fast memory called SRAMM. Materializing an intermediate attention matrix for 100,000 tokens requires hundreds of gigabytes of memory. Reading and writing this massive grid between the slow HBM and the fast SRAM entirely saturates the memory bandwidth, stalling the GPU entirely. This diagram shows the mathematical solution, flash attention, driven by the online Softmax algorithm. The equation introduces the variables mnew and lnew, applying an exponential correction factor dynamically to a running sum. A standard Softmax calculation requires scanning the entire global sequence multiple times to find the maximum value and the normalization denominator. Online Softmax bypasses this dependency, continuously tracking a local maximum and updating a running normalization constant. This iterative approach allows the attention matrix to be processed in localized tiles directly inside the SRAM. By updating running max and sum variables on the fly, memory complexity drops from n squared to linear without ever materializing the full grid in HBM. Flash attention effectively neutralizes the quadratic memory explosion within a single chip. But to reach extreme million-token context lengths, the sequence outgrows the physical limits of a single processing node entirely. When sequence dimensions scale into the millions, the intermediate attention matrices outgrow even the partitioned memory architectures of standard sequence parallelism. To push further, training systems deploy context parallelism. One method, DeepSpeed Ulysses, relies on an incredibly fast all-to-all communication topology. It dynamically transposes the layout, gathering scattered sequence fragments so each GPU receives the complete sequence, but strictly for a specific, non-overlapping subset of attention heads. Ulysses is exceptionally fast, but it is mathematically constrained. Because it distributes attention heads across the cluster, the degree of parallelism can never exceed the total number of heads. If you have more GPUs than attention heads, the system physically breaks. Ring attention bypasses this head count limit by modifying the mathematical execution. It organizes the participating GPUs into a circular peer-to-peer ring topology. This circular node graph illustrates the execution. During the forward pass, a GPU calculates scaled dot product attention using its local token blocks. Simultaneously, it transmits its key and value blocks to the next device in the ring, while receiving new blocks from the preceding device. Because the point-to-point communication of the key-value tensors is perfectly overlapped with the dense matrix multiplication of the attention computation, the transmission latency is effectively masked. The network overhead becomes virtually invisible. This architecture removes the final physical boundary of context length. But as AI models grew, that tiny cable became a massive traffic jam, physically capping how fast a system could learn. To get around this, data centers had to string hundreds of these discrete server nodes together. It worked, but it required pushing data through external network cables, introducing significant delays every time the chips needed to talk. NVIDIA solved this physics problem by engineering the GB200 NVL72. They removed the PCIe bottleneck entirely and connected 72 GPUs using NVLink, a unified copper backplane capable of moving 130 terabytes of data per second. Because this backplane is so fast, the CPUs and GPUs no longer have to translate or copy data back and forth. They share it instantly. The entire rack now operates as a single coherent computer with a staggering 30 terabytes of unified memory. The defining unit of high-performance computing has scaled up. The boundary is no longer the individual silicon chip. The entire physical rack is the computer. When you load an efficient AI model, like an 8 billion parameter version of Llama 3.1, onto this rack, something highly unusual happens. The core weights of that model take up less than 1% of the rack's total memory. Engineers take that massive surplus of leftover memory and use it for multidimensional parallelization. This is the process of slicing the math into distinct pieces, distributing the model's layers and sequences across all 72 GPUs simultaneously, so they can process enormous batches of data without waiting on each other. Training an AI of this size from scratch on a massive dataset used to require data center halls full of hardware and years of continuous runtime. On an NVL72, that exact same training run is completed in 3 to 7 weeks. At the 8 billion parameter scale, the NVL72 provides absolute hardware abundance. The math maps cleanly to the physical topology, and the entire workload is contained perfectly within a single rack. The artificial intelligence industry operates on a ruthless scaling curve. While an 8 billion parameter model fits beautifully into one rack, laboratories are aggressively building frontier models that exceed 400 billion parameters. This chart shows the memory wall these frontier models hit. Even though a single NVL72 holds 13.4 terabytes of ultra-fast VRAM, a 405 billion parameter model requires over 800 gigabytes just to store its base weights. Once you add the dynamic memory cache required to process long context windows, the data footprint instantly overflows the maximum capacity of a single rack. To train a model this massive, engineers must bridge anywhere from 70 to hundreds of NVL72 racks securely together. They use highly specialized InfiniBand networks to handle the overflow, essentially creating a secondary highway system between the discrete racks. Pushing the limits of machine intelligence forces you to break the physical boundary of the rack. At this scale, the data center has to be orchestrated to act as one cohesive machine. Packing this much processing power into a confined space creates an extreme thermodynamic problem. Under load, a Blackwell GPU die produces an immense heat flux that is more comparable to a nuclear reactor fuel rod than a traditional computer chip. A fully loaded rack pulls up to 135 kilowatts of power. You physically cannot blow enough air across the chips to keep them from melting. Running these systems requires vacuum-brazed copper cold plates explicitly piped directly to the silicon, pumping 80 liters of liquid coolant through the rack every minute. The fluid and metal density pushes the weight of a single rack to 3,000 pounds. Dropping a multi-rack cluster into a building requires specialized structural concrete flooring just to keep the machines from crashing through the floor. Getting your hands on this specific hardware requires massive capital. Driven by tight memory supply chains and advanced manufacturing, the next-generation Vera Rubin rack is projected to cost $8 to $9 million per unit. Building a frontier AI laboratory is an exercise in extreme physics and multi-billion-dollar capital expenditure. Most modern enterprises find themselves caught in a dilemma. They need advanced AI to remain competitive, but they cannot justify hundreds of millions of dollars in capital expenditure and facility retrofits to build a liquid-cooled supercomputer. While the major tech companies are locked in an arms race over data center thermodynamics, the future of enterprise AI relies on a different strategy. It comes down to renting the exact amount of high-speed compute required to solve a business problem, right when you need it.